Hi, I'm happy to present my work with Srihari, Govindan and Pahl in this EC'20 event on sustainable equilibria. Sustainable equilibrium is an equilibrium notion, refinement of Nash equilibrium, defined by Roger Myerson in 1996. It was defined informally and more by the properties that he wants this notion to satisfy. For example, Myerson wants that any sex equilibrium be sustainable. Also, he wanted that not all equilibria be sustainable. For example, in the battle of the sexes, he wants that only the two strict equilibria are sustainable, but not the mixed equilibrium. He also wants that if a game has a unique equilibrium, then it is sustainable, and that almost every game has a sustainable equilibrium. Hofbauer expanded on Myerson's idea and tried to formalize this notion of sustainability. He defines an equivalence relation among pairs, games, game G, and a strategy sigma, which is an equilibrium of G. A pair G sigma will be equivalent to a pair G hat sigma hat if sigma is equal to sigma hat up to a reliability of strategies, and if we restrict G to the best replies to sigma, and if we restrict G hat to the best replies of sigma hat, then these two games are the same game, up to reliability. An equilibrium sigma of a game G will be called sustainable, according to Hofbauer, if and only if G sigma is equivalent to G hat sigma hat, such that sigma hat is the unique equilibrium of G hat. In particular, if sigma is the unique equilibrium of a game G, it will be sustainable according to this definition, because a game is always equivalent to itself. Let me give you an example to illustrate the idea. Here is a Battle of the Sexes game with two strict equilibria, Nash pure equilibria, sigma and theta, TL in red and BR in red. Let's construct a game G hat such that TL is the unique equilibrium. To do this, we add strategy X to player 1, strategy Y to player 2, the row player, the column player. In this new game, larger game, strategy B becomes strictly dominated. 0 is smaller than 1, 2 is smaller than 4, -2 is smaller than -1. So X strictly dominates B, Y strictly dominates R, B and R are eliminated. And now X becomes strictly dominated by T, Y becomes strictly dominated by L, and now TL is the unique equilibrium, implying that sigma is sustainable. We can do the same for theta, but we cannot do the same for the mixed equilibrium of this game, which implies that it is not sustainable according to Hofbauer definition, which is in line with Myerson's definition of sustainability. You may think that this is the case only because the mixed equilibrium is a mixed equilibrium. In fact, in this game, we can make the completely mixed equilibrium unique. So this is a game with 3 strict pure equilibria in red. There are also 3 other mixed equilibria where players are mixing between 2 pure strategies. For example, 1/2 T, 1/2 M, or 1/2 T, 1/2 B, or 1/2 M, 1/2 B by symmetry. These are 3 equilibria which support 2. There is a completely mixed equilibrium which support 3, 1/3 T, 1/3 M, 1/3 B, 1/3 L, 1/3 M, 1/3 R, which is another equilibrium of this game. We can make the strict equilibria unique, so they are sustainable by using the same trick as in the other example, but you can also make the completely mixed equilibrium unique. To do this, we can add 3 strategies, X, Y, and Z, as in this example, which kill all other equilibria in this game except this equilibrium, the completely mixed equilibrium. This construction is not obvious, and it used polytopes. It was done in the PhD thesis of von Schemed with Bernard von Stengel. What is interesting also is that the 3 remaining mixed equilibria of this game cannot be made unique because I will explain this later, and I'll let you think about the proof of this. So, for example, 1/2 T, 1/2 M, 1/2 L, 1/2 M is a mixed equilibrium which supports 2. And it is not possible to add strategies to this game to make this equilibrium unique. So not all equilibria of a game are sustainable. So now what are the sustainable equilibria? So let me give some definitions first. Let's the set of players be capital N. The pure strategy set of player N is Sn. The pure strategy profile is capital S. Product of Sn. The set of mixed strategies of player N is denoted by sigma N, and sigma is the product of sigma N, and it is the set of mixed strategy profiles. S minus N, sigma minus N, sets of strategy profiles of player other than N, pure and mixed. And the pair function G is defined in R to the power N, and the N component is the pair function of player N. So this defines a game. Now, as we are going to see in the next slide, sustainability has to do with the index. So now let's define the index of an equilibrium. Let U be a neighborhood of sigma. So this is an open set which contains the set of mixed strategy profile. Take a differential map such that the fixed points of this map are the Nash equilibria of G. A Nash map, for example, the one that Nash used to prove existence of Nash equilibria. Is one particular case. Take the displacement map, which is sigma minus f sigma. So d sigma equals 0 are the sigmas that are Nash equilibria of the original game, because this implies that sigma is equal f sigma if the sigma is 0. Now call a game regular, or call an equilibrium regular if the Jacobian of this displacement map at sigma has a non-zero determinant. Okay, it is non-singular. Now, call a game regular if all Nash equilibria are regular. And now define an index for an equilibrium to be plus or minus 1, depending on the sign of the determinant of the Jacobian at the displacement map, which depend on f. What is important is that this is independent on f, in fact. There is a general result in game theory saying that the index of an equilibrium is independent of the map f that is used. Now the Hofbauer conjecture says that a regular equilibrium is sustainable if and only if it has index plus 1. This was stated in 2000, and it was proved for two-player games in 2008 by Van Schiem and Van Stengel using polytopial geometry. Our paper proved it for n-player games using algebraic topology, and I'm going to explain the proof in the next slide. The two first corollary that we can have, given this, the fact that this is true, is the following. First, since the sum of indices of equilibria is plus 1, which is a general result in game theory, we know that any game has at least one regular equilibrium which has index plus 1, which implies that any game in a regular game has at least one sustainable equilibrium. Also, we know from general results in game theory that set of regular game is an open dense set in the set of games, which implies that almost all games have a sustainable equilibrium, which is what Meyerson wanted. Now the proof, let's do the easy part of the proof first. Suppose sigma is a regular equilibrium of a game G. And suppose that sigma can be made unique in an equivalent pair G bar sigma. We want to prove that the index of sigma is plus 1. Let G star be the game obtained from G by the latent inferior replies to sigma. From a general property of the index, we know that the index of sigma in G can be computed as the index of sigma in G star. In fact, since the game is regular, the G star is the game where we restrict ourselves to the support of sigma. This is not true when sigma is not a quasi-strict equilibrium, but since the sigma is regular, it is quasi-strict. And so G star is just the game when we restrict ourselves to the support, and the index of sigma can be computed from the index in G is the same as the index of sigma in G star. But G star is also the game obtained from G bar by the latent inferior replies to sigma, which implies, in particular, since sigma is regular, that sigma is quasi-strict equilibrium in G bar. Therefore, the index of sigma in G star is equal to this index of sigma in G bar according to this property of the index. But since sigma is the unique equilibrium for G bar and the sum of indices is +1, it must have index +1 in G bar, so it has index +1 in G star, so it has index +1 in G. So now let's do the other direction. I give just an idea about the proof because it's much more complex to explain in few slides. Suppose G is a regular game and sigma is an index +1 in equilibrium, and we want to show that we can add strategies to sigma, to G, so that the unique equilibrium remaining is sigma. So we want to kill all other equilibria as in the examples before. Since the sum of indices over all equilibria is +1, the sum of indices of other equilibria is 0. Now take a map, Nash map, whose fixed points are the equilibria of G, and change this map outside U, such that the unique equilibrium of this new map F0 is sigma. And so there is no other equilibrium other than sigma, so there is no other equilibrium outside U. This can be done thanks to Hopf extension theorem, and let's illustrate this result in an example. It's a 2x2 game, symmetric game, and we are restricting ourselves for simplicity to symmetric strategies. Symmetric profile is represented by a number x in 0, 1. There are two pure equilibria, x equal 1 and x equal 0, strict equilibria with index +1, and one mixed with index -1. The Nash map in this example can be computed as follows, and this is the black map here, which intersect the diagonal in 3 points in red, which are the 3 equilibria. The +1 index are the 2 extreme, and here in the middle is the -1. In green is the new curve, the new map, which is equal to the original map in the neighborhood of the equilibrium, and non-equal to it outside the neighborhood. And this map intersects the diagonal only in the equilibrium that we want to make unique. Now the challenge is to construct a game such that this map is the best reply on the best reply function in this game. So we want F0 to be kind of best reply function of a game. The first problem is that F0, if you take the n component, which corresponds to player n, this F0n depends on all the strategies of all the players, including player n, but in a best reply function, it depends only on the other player's strategy, sigma minus n. So to solve this problem, we construct an equivalent game G tilde from G by adding what? By adding some strategy that will be irrelevant for payoffs for the given player. So here, player n in the new game G tilde have a strategy set, pure strategy set S tilde n, which is Sn product with Sn plus 1, n plus, which is the player next to him. And here we player capital N plus 1 is player 1. And now we can construct a new function f tilde 0n in this, which goes from sigma tilde minus n to sigma tilde n. Given the strategies of the other players, this is the best reply somehow in this game G tilde. And the choice of player n minus 1, the second coordinates irrelevant payoff for him will be what player n will play will play, and we put this in F0, and then we compute using F0 the value of f tilde 0n. Now what we do is in this equivalent game G tilde, we'll take sigma tilde n, the strategy set of player n, and we take a triangulation of this set. We take a particular triangulation, Delaunay triangulation, because we will need it to construct for its nice properties. We add the vertices of the triangulation to the original game G, and now we associate payoffs to these new strategies, new pure strategies, using this map f tilde. And we use the fact that F0 doesn't have a fixed point outside U to deduce that the game where we add these new strategies will have only one equilibrium, our original equilibrium. Somehow what we have is something like that. Our game strategy set is this one. this is our example of the symmetric game with symmetric equilibria. Player one has one of the player one, for example, has strategy set 0-1. We add to it duplicate strategy, which is the strategy of the next player to him. Now we have the strategy set, which is the square, which is the strategy set in the game J tilde. We do a triangulation, and we take the vertices of the triangulation. We add them as strategies on the original game. And then the payoff is the payoff of the original game, and F tilde will give us will be used to construct payoff for these strategies, so that this green point here will be the unique equilibrium of the extended game, which will imply that our +1 index equilibrium was made unique in the larger game, and which finishes the proof of the theorem. Let me finish with an example, and this is a 2x2 game. This is between two players, and we have a dummy player which has only one action, but then we'll add to this player some actions. This game has two strict equilibria with index +1, one mixed equilibrium with the index -1, and according to the results before, the -1 equilibrium cannot be made unique in an equivalent game to G. The fact is we can enlarge this game and have a larger game in which sigma is the unique equilibrium. The -1 equilibrium is the unique equilibrium, which is kind of contradictory. It is not, because the G sigma will not be equivalent to G bar sigma, G hat sigma, because sigma will not be quasi-strict in G hats. So here is the example in the next slide. So this is our original game. We add the strategies to the players. Now we have a larger game. The 1/2 equilibrium here gives to player 1 and 2 the payoff of 3. This implies that now if player 1 deviates to B, he will get also 3, or player 2, if he deviates to I, gets also 3. This means that the equilibrium 1/2 here, 1/2 here, and player 3 is playing this matrix, is not a quasi-strict equilibrium in this large game, which implies that the game G, our game G hat, is not equivalent to our game G at sigma. So it is, if it is true that you can make a -1 equilibrium unique by adding strategies, it is not the unique, it is not quasi-strict, and so the two games are not equivalent. So thank you for your attention, and hoping to have now your questions.